transition come.
Thank you. Thank you for the invitation and the opportunity to speak here. So unlike what's written in the printed program, I'm not Andrei Bernovic. But hopefully he'll be here. I definitely hope to hear from him. So this is more or less the plan of 2 lectures. Instead of saying it in words, I'll show you some pictures right here. So I'll just talk about some phenomenology, some experiments, covering some history of this subject of quantum transitions, and then I'll switch to some models and theoretical developments that happened more recently. So here's the first thing, of course, that you know. I mean, you put a 2-dimensional electron system in a strong magnetic field, you measure the longitudinal and transverse voltages, and you can plot them as a function of the magnetic field, and we saw this plot in Janendra talk. What is amazing is that the quantization of the whole resistivity of the plateaus is amazing. It's like 1 part in a billion. And in spite of the fact that the samples look literally like this, or at least original samples look like that, how could you expect such a quantization from such a horrible device, right? So, and we know that it's explained more or less by topological reasons in some sense, right? So topology makes this very robust, and it's providing some universality to this result. Now, so as already was mentioned, disorder does play a huge role in here. So I just want to emphasize it right here, that if you didn't have any disorder in a clean system, any clean system, no matter interactions, no interactions, whatnot, you would choose just to see a straight line for the whole resistance. It just follows from Galilean invariance, and you would not see any plateaus. Even if you have some well-formed quantum pole states, you would still not see anything like on this trace, okay? So disorder does play a huge role in developing these states, and we'll talk about this a bit later. Now, so I will focus mostly on the transition between the plateaus. So this transition also shows some universality. Well, at least we believe that it could be described by some universal physics. And so that's what I'm going to be focusing on. By the way, I prefer, if you have any questions, don't hold on to them, just ask them when I'm speaking, okay? So don't wait until the end of the talk. All right. So, so the history is that, of course, in the low mobility, the semiconducting heterostructures that were used in the early days of this story, you see only integer fractions described by these values of whole resistivity, and where I is an integer. And so the story here is that the disorder, the role of the disorder is that essentially electrons, for the quantum Hall states at integer fractions, you more or less can explain them by the non-interacting physics, right? And so you can think about just single electron moving in a random potential and strong magnetic field, and then most of the energies correspond to localized states, and only certain energies correspond to extended, more or less extended states, and that's what explains the existence of these plateaus here. Because localized electrons cannot carry current, and so the current only flows along the edges where the confining potential allows for the electrons to flow. All right. Anyway, so one interesting story here is that these days, this phenomenon is used to define the resistance quantum and even fine structure constant and the kilogram, as you may learn from Veritasium videos. Beautiful story how fundamental physics has allowed to redefine the definition of kilogram, going away from an artifact kept in Paris to some apparatus that is measuring fundamental physics. All right, so one other thing that it will be important later is that in 2 dimensions, resistance and resistivity have the same units. So when you think about how to relate them, usually even for longitudinal resistance, you would have the ratio of the area, cross-sectional area, and the length of the sample, right? But here in 2D, both the area and the lengths have the units of length. So in that sense, these things cancel out, and that's why I have the same units. And it sort of carries on to the critical point that we're going to be talking about. All right. Now, if you go to low temperatures and high mobility samples, you see all these beautiful structures developing, all these fractional states, and even denominator fractions and so on. And now everything is characterized by a relatively simple fraction multiplied by the whole resistance quantity. All right. Now the important thing here is that already in this picture you see that things depend on the temperature in a rather non-trivial way. I mean, it's not clearly seen here on this plot, but for the longitudinal resistance, you see that the minima of the resistance become deeper and deeper as you lower the temperature, right? So there's some temperature behavior here that needs to be understood. And even more pronounced, if you really look at how the integer transition looks like at different temperatures, you see that the transition is smeared by a finite temperature. It becomes sharper as you lower the temperature, and the peaks in the longitudinal resistance also become narrower as you lower the temperature. And so if you plot now the steepness of this step here, namely the maximal value of the derivative of the whole resistance with respect to the magnetic field, on a log plot as a function of the temperature, you see a straight line. And this has been seen for a long time, since early experiments in the late 80s. And you can extract a number here, the kappa number, that was measured to be about 0.4 in these early experiments. Okay, now seeing such scaling, as I call it, right, is reminiscent of scaling phenomena near classical critical points, classical phase transitions, continuous phase transitions, except that for the Ising model, let's say, when you plot magnetization of the function of temperature, it's T minus Tc that is raised to some power, right? Here, Tc is 0, which means that we are dealing with a quantum phase transition at 0 temperature. Okay, and that's the basic view of this phenomenon that I'll be emphasizing and talking about. All right, now, so you can also look at the direct transition between some fractions, like 1/3 and 2/5 here, and you also observe the same kind of scaling. What's amazing is that the number in this scaling comes out to be more or less the same as in the integer transitions, okay? Which is completely unexpected. This is, I mean, definitely a different story, but nevertheless, that's what you see. Now, what about, so when we have some continuous phase transitions, we very often talk about universality, how the emergence of long length scales kind of hides all the microscopic details and makes them unimportant, and everything is then governed by some universal physics, right? So here, the question of universality has been coming up again and again and again and again. And the reason is that different samples, actually people have gone through, you know, hundreds of samples and of different types and different systems. And some of them show different scaling, meaning that numbers here can deviate from 0.42 quite significantly. And so some people have not even seen scaling at all. They saw some activated type exponential behavior. So it was not clear what's going on. So Densui's group decided to take these matters seriously, and they studied a system where they could distinguish different types of disorder, not only in just quantitative terms, but like by changing these concentrations of impurities, but qualitatively. They could go from undoped semiconductor on one side of the heterostructure, where they would have some ionized impurities that would provide long-range correlated disorder, to some other concentrations where the disorder mostly was short-range, and then ultimately for very large concentrations of X, the impurities started to clump into, some clusters, and that also changed the behavior. So the upshot of this story was that the claim of this paper is that once you can control disorder and make it short range, then you should see an universal scaling with this 0.42 power, okay? But this has been questioned, and so this was already in 2005. In 2009, they had very beautiful set of experiments where they, so this is just one step between the integers 3 and 4. And you see that the traces at different temperatures intersect at a single point. That's, exactly an indication of some kind of a continuous phase transition. So what they did, they managed to plot this thing. Well, so, okay, maybe I should backtrack a little bit. So when you see such a plot here, original plot in the in here, well, you see that the range of temperatures is between 0.1 Kelvin and 4 Kelvin. It's 1.5 decade, less than 2 decades, certainly. So when you claim to have seen a scaling behavior, typically you would want to have more range, right? And nowhere. So in the history of critical phenomena, the best studied critical point is probably lambda point in liquid helium, where people managed to, they even had to worry about stratification due to gravity on Earth to think about this critical point. So they sent the samples to space and measured critical exponents very precisely by, having enormous dynamical range in this scaling variable. But that led also to some mysteries that I'll mention next time. All right. So here you see that the scaling, you see, 1 decade, 1.5 decade at most. So what these people did, they went to MagLab, right? And ran it in the dilution fridge and managed to go to single millikelvin. So it's not shown here, but I will show it later. So when I was preparing this lecture, I realized I was going to MagLab, and so I was wondering, so why is this Gainesville and I'm in Tallahassee? So I had to ask ChatGPT what happened. And apparently there are 2 campuses of MagLab, which I didn't know about. So one of them is in Gainesville and the other is here. And this experiment was done in Gainesville. All right, and so here you see 2 decades or more of this beautiful scaling. So this quotation from the paper, perfect scaling to 2 full decades of temperature from 1.2 Kelvin down to 12 millikelvin. All right. So you see this number. In fact, when they looked at the samples which were outside of this range of short-range disorder, they showed scaling with other exponents at higher temperatures. When you went to this super low temperatures, they still crossed over to the universal scaling. So even nominally long-range disorder eventually becomes short-range if you can maintain phase coherence such that the phase breaking length is longer than the correlation length of the disorder. Then you do become short-range de facto, and you cross over to this universal number again. All right. So now these days, of course, people are doing everything on graphene, and graphene shows quantum pole states, obviously, and people have seen transition between the states and studied them. One of the most recent papers in this respect is this paper from Bid's group in India. And so they managed to observe and measure many, many different transitions. And what's interesting about this paper, they measured not only transitions between integer plateaus and fractional plateaus, but also direct transitions from fractions to integers, and they all show the same behavior. So that's a remarkable statement. So for example, here, this transition to integer plateaus with this exponent, well, 0.4, not 0.42, but okay. This is some fractional transition. This is the what's called scaling collapse plot for this type of behavior, right? Which is a typical story when you have some scaling behavior near a critical point. You can rescale things. The difference between in this case, the ratio of the all resistance and the value of the critical point can be plotted as two branches on the left and on the right of the transition by, scaling with a certain. So the deviation from the critical point should be scaled as some power of the temperature to allow for this, all the data fall onto a single curve, essentially. And again, this was sort of another way of extracting this exponent kappa by trying to see what power of t should be taken here to obtain a Wild scaling collapse. And so this is their results. So you can see that there are integer transitions, integer to fractions, fractional transitions, and so on. They all show more or less the same behavior. And this scatter here is other previous studies from many, many other systems. But again, so the claim is that these deviations from this universal value are due to, well, when people say long-range disorder, again, ultimately, if we manage to cool the system down to extremely low temperatures, this all should cross over to universal scaling once the phase coherent length exceeds the correlation length of the disorder. All right. Now, so let me go through some basic theoretical picture of this story. So as I said, these should be thought of as quantum phase transitions in zero temperature. So let me go through some basics of quantum phase transitions. For simplicity, I will set these units to 1. So a quantum phase transition is something that happens in the ground state of your system at zero temperature as you vary some coupling in your Hamiltonian, right? So you can imagine probably the easiest system to think about is the transverse field Ising model, where you have a spin chain with a transverse field applied to it. And so when the coupling between the spins is strong, they're ordered in the z direction. When the transverse field is strong, they're ordered in the x direction. So and this is a competing type of interaction. So these two terms in the Hamiltonian do not commute, and one of them wins or the other wins, depending on the ratio of the couplings, right? And so as you vary this ratio, you have a change in the ground state, which happens continuously, actually. In that case, that transition is exactly in the same universality class as the 2D classical Ising phase transition. So these transitions are accompanied by the appearance of diverging length scales. And these length scales are behaving as power laws of the deviation of the coupling from its critical value. So let me call this delta is the distance to the critical point. And this nu, unfortunately, it's one of the cases it's most severe in mathematics, but in physics it's also the case that we don't have enough letters in all the alphabets that we can think of to represent all the quantities we want. So this nu is not the filling fraction that was before. Now it's some universal critical exponent called the correlation length exponent. Okay. Now, in a quantum system, the behavior in space and behavior in time are very strongly tied together. So you cannot really separate them. So what happens is that in addition to the diverging length scale in space, there's also a divergent temporal scale, where the quantum fluctuations are correlated. If they're correlated in space, they're also correlated in time. And this time scale is also large, diverging as you approach the critical point, and the scaling between the two things is characterized. So the temporal scale diverges as a different power of the distance to the critical point, and there's a exponent z called the dynamical critical exponent that relates to 2. Okay. Finally, I want to mention that this temporal scale can be thought of as the inverse of some characteristic gap in the spectrum, at least on one side of the transition, that is closing as you're approaching the transition. So you can also think about this gap closing as having some scaling form. All right. So this z is an important quantity that kind of, whenever you have some scale in the system, maybe imposed from the outside, like a finite size system or some frequency or some electric field or whatever, they introduce both temporal and spatial scales, which are related by this dynamical exponent. So that's important to know what that is. All right. And so once you have these diverging scales, they determine the scaling forms of all measurable quantities, all observables. So suppose you have some quantity that they can measure, some correlation function that maybe has some finite wave number, some finite frequency. K is the coupling constant. And so what happens at the closest transition point, this observable takes a scaling form. Namely, it's mostly a power law of the correlation length. That's the only scale we have in the system at that point. And the power here is what's called the scaling dimension of this operator that they're looking at. More often than not, the scaling dimensions can be roughly estimated from naive power counting in the Hamiltonian or the action of the system. But very often, and usually, at the critical point, this is different from the naive scaling dimension. So one has to sort of struggle and work hard to find out what this number is. Not the case with the quantum clock, luckily. Okay, and this is what's called a scaling function whose arguments are dimensionless ratios of or products in this case, of the, let's say, the wave number and the correlation length or frequency and the temporal scale. All right, and so once we think about these phase transitions, the main goal of the theory would be to find out those universal numbers, the critical exponents, and scaling dimensions or operators. All right, so now what happens at non-zero temperature? So far I've been working at zero temperature, right? When you introduce the temperature, what happens is that immediately there's some length scale appears in temporal direction. So the best way to think about it is that once you think about a quantum system, you can write its partition function at the finite temperature, e to the minus beta h trace, right, as some kind of path integral. There's some representations from the path integral, and at that representation, the time direction just serves as another direction. So you can think of that system effectively d plus one dimensional. If you study with d-dimensional quantum system, this effective description makes it d plus one dimensional. And now, if you have zero temperature, this extra dimension is stretching indefinitely, it's infinite. But once you work at a finite temperature, this dimension becomes finite. And so you have to impose sort of periodic boundary conditions or anti-periodic boundary conditions in this dimension. So it becomes, the whole system becomes a torus with the finite lengths in this in this temporal direction. And so then what happens is that you have to think about the competition between the scales in this direction. So this temporal diverging length scale far away from the transition is shorter than this finite size of the system. And so if you're far from the transition, the system has not yet realized that it's finite in this dimension, and you behave like you were at zero temperature, more or less, right? But as you approach this critical point, these length scales grow, and eventually your time direction the divergent length in time direction hits this wall, and it doesn't matter anymore what it is. In fact, everything is cut off by the system size at this point, and the system then kind of realizes that it's actually in d dimensions than v plus 1 dimension. And so this is all effectively encoded in what's called a finite size scaling theory, where in addition to the usual scaling with the correlation lengths or temporal scale psi sub tau, you also have to add the scaling parameter, which is determining the ratio of the size of the system in the temporal direction and this temporal correlation lengths. And so that leads to some temperature scaling. The physics behind this is that you can think that the temperature destroys quantum coherence at some scale. And we call it dephasing, and I'll comment on this a little bit later, what's going on here. So there's some crossover scale determined by the condition that this psi tau is equal to this size and temporal direction. And the quantum fluctuations that are in below this scale, they're quantum, but beyond this scale, they behave classically, essentially. And you can also introduce the dephasing rate, which is related to the temperature in a simple way, according to this simple scaling ideas. So I want to make a caveat here that this whole story is about what's called generic quantum critical points. In fact, there's something that I will be talking a bit later. There are interesting quantum critical points, including some quantum fold transitions, which are not like this, okay? And so this is something that needs to be understood better. And the caveat here is that the interactions that are present in the system can be sometimes thought of as perturbations on non-interacting physics. And in that sense, you can ask whether they're relevant or irrelevant at a fixed point describing non-interacting transition. And then if they're relevant, they sort of grow and saturate at the critical point, or maybe go to infinity even, or in some sense. And that is the generic quantum critical point, where interactions are important. They are really destroying the single particle physics that underlies the description of the non-interacting systems. And it's like a soup of excitations which cannot be thought of as quasi-particles anymore, right? And in this case, that's what we see. But in some other cases, the single particle physics still survives and the interactions are irrelevant. They still modify the scaling. And that's the interesting story that I'll talk about a little bit later. All right. So now let me see how these ideas apply to the integer quantum Hall conditions. Okay, maybe going back to this general scaling story here, you see that the dimension of the operator propagated through these formulas. One thing I forgot to mention, sorry. Once you have more than one argument in the scaling function, you can always trade them for their products or powers and so on. So you can sort of play games where you rewrite things in a different way. For example, this psi could be traded for the LT through the combination of scaling variables here. And so there's no unique way of writing a scaling function, a scaling form. And some forms are better than others. So you sort of have to sort of play with this and get used to this different scaling form. All right. So when you go to the description of the longitudinal and Hall resistances and the resistivities of the quantum path, I want you to remember what I said earlier, that resistivities and resistances have the same units. And since the basic observable has a value that is more or less given by the resistance quantum, determined by fundamental constants times a pure number, it sort of may indicate that dimensions, scaling dimensions of those quantities are actually zero. And that's what you see experimentally as well. I mean, the values of the resistances at the critical points, both the longitudinal and whole, are just numbers, right? They're not moving, right? When we saw the some kind of let's see, do I have it here? No, I don't. So let me go back. So in these traces, right? So if you set exactly the critical point, the resistance is just not moving. It's a number, right? So that's what we mean by the zero-dimensional nature of this thing. So there's no dimension to the whole resistivity and longitudinal resistivity. That's why we have no prefactor here, just the scaling function itself. Now I combined here, so I expressed everything in terms of the temperature, having this freedom of trading various arguments to their powers or their ratios and products and so on. So I can always replace this temporal scale by, or due to this presence of this ratio of the size of the system in the temporal direction and the diverging scale, I can trade this size for the temperature, right? And that's what I did here. So now, having this form, I can just see how we can interpret the experiments I was showing you so far. So let's think about the DC transport. So we set omega to 0, so we get only one scaling argument here. And then once you see this form, it immediately follows that f has some shape. It's supposed to be some universal function. We cannot typically compute it, but it's some nice function with some scale in its dimensionless argument. And then that translates to having some scale in the delta B, which is the width of the transition, or the slope of the step. And that's supposed to be, just looking at this thing, you realize that this behaves as a power of the temperature with the kappa that is given by 1 over z times net. So this is how this scaling in the transition is explained from the point of view of quantum critical points. Now you can also do scaling in the opposite region when you can impose AC signal on your system and think about what happens at frequencies which are larger than the temperature. Then you can, trade you can essentially behave like a zero temperature. So you can remove the temperature from here by finding the appropriate ratio of these two scaling arguments, and that's what you get. And then you predict that the width of the transition should behave like the frequency to the same power. And so this is indeed observed in some experiments, multiple experiments really. And what's interesting here, you can see the same scaling, the same power law. And you can also see that the crossover phenomenon that is should exist at the frequencies of order of the temperature is also seen here. So when you see, I'm not sure I can see the numbers here, but I see them on the screen here. So so this is 50 Kelvin, millikelvin, this is 200 millikelvin, and this is 470 millikelvin. So at high frequencies satisfying this condition for all temperatures, you see this scaling behavior, but then these traces start to peel off. And depending on the temperature, they peel off at different places, right? And that's exactly the crossover temperature that should be related to the frequency here. And that's what you see in this plot. So this is a beautiful confirmation of the, in fact, you can analyze this data using the two-parameter scaling form with this scaling function. Now, once you see this combination, the natural question to ask is, can we separately measure nu and z? Because so far they have appeared in the combination, and we would like to know them separately, right? So there are tricks to do that, and one of them was the continuation of this story of this heroic effort to go to single millikelvin. So what happens is that if you continue this from 10 millikelvin to 1 millikelvin, the trace actually stops growing. It saturates to a constant. Okay. So that's what's observed at the lowest temperatures. And what happens, so the interpretation of this is that the sample, as you cool it down, becomes more and more phase coherent, right? And the phase coherence length, or phase breaking length, if you want, grows as you lower the temperature. And at some point, it becomes comparable to the sample size. So that's when the whole thing, this L phi, should be traded for the W in the scaling functions as the width of the sample, and that's what rounds off this temperature dependence, okay? And then what the experimentalists did, they prepared several samples cut out from nominally the same wafer and of different sizes between, I think, well, the 100 micrometers and more than almost 200, 2,500 micrometers. And they plotted the position of this crossover temperature as a function of the width of the sample. And again, on a log-log plot, they discovered that this is a scaling form with the power 1. Okay, so that sort of tells you that z equals to 1 and this transition. Now, z equals 1 is actually very special. So there are several reasons for this to be special. One reason is that it's believed to be coming from strong Coulomb interaction. So strong Coulomb, long-range Coulomb interaction generically is believed to lead to critical points with z equals 1. From a theoretical point of view, it's interesting because if z equals to 1, then the temporal scales and spatial scales are on the same footing. So you're dealing with a d plus 1 dimensional system where time is not different from space. So if these are critical points, which are scale invariant, maybe the scale invariance is promoted to conformal invariance, and then we have a conformal field theory that should describe this critical point, right? So quantum Hall transitions should be describable by some three-dimensional conformal field theory that we have no clue about, really. Right? So that's a challenge for the bootstrappers and whoever else can do it, probably, right? Okay. So now you can also do the following trick. You can also look at the nonlinear response of the system to at high electric fields or currents. And then what happens is whenever you have new variable, new knob in your apparatus, typically introduces its own length scale. And so the electric field is introducing a new length scale in the spatial direction and the corresponding temporal scale. And at t equals 0, this should replace the dephasing scales at finite temperature. And so the way to find this LE is just to compare the typical energy of an electron that moves across this spatial length to a typical energy related to this temporal scale here, right? And so this gives you some scaling of that length with the electric field. And once you trade the phase breaking length to this length here, you get this scaling form, which predicts some behavior of all observables as functions of the electric field. And notice that in this case now, I have the different conditional exponents here and here. And so in principle, I can figure out, separately measure the product of z nu and z plus 1 a, right? So then you can look at the current scaling at temperatures which are below this crossover temperature, and you should see that the scaling of this maximal value of the derivative and the plateau, and transition widths should be scaling with the electric field with some power that is now not 1 over z nu, but 1 over z plus 1 here. And so this is what's observed in these experiments. So you can plot these things as a function of the current and extract this value here. So together with the previous measurement of the kappa, temperature scaling, you get z equals 1 and mu equals, so consistent with the previous experiment. Now, one interesting thing here is that if you just compare two pictures here, so this is a picture taken at very low temperature and at low current, but different temperatures. So you see the smearing of the step and broadening of the peaks in the longitudinal resistance. And then the lower picture shows the fixed base temperature of the refrigerator, but different currents, much larger currents than here, right? And you see the same phenomenology. The steps become broader for larger currents, and the peaks become broader for larger currents. So in some sense, the current can be translated to an effective temperature. You can sort of compare these two pictures and say, okay, I can think of this smeared step as coming from some higher temperature. So in some sense, this is what happens. I mean, if you drive the current through the system, it heats it up. And then if for some reason the phonons are not there to take this energy away, there's some bottleneck in the equilibration, then the electrons in your system are effectively heated up, and then that's what you see. So this is one of the interpretation of this story, and you can sort of think about this crossover temperature as an effective electronic temperature, and you literally can measure it and plot it again as a function of the current, and you see the same type of scaling behavior with this exponent now, which is extracted to be 0.5 essentially, so z equals to 1. And you also see this peeling off at different temperatures due to the crossover, right? All right. Now, so here's the quite a bit more complicated story about relevance of interactions. So here's I should sort of say that so far I've been discussing this very phenomenological approach based on scaling ideas of quantum phase transitions. But historically, this field came out of what's called mesoscopic physics, where people looked at low temperature transport in smaller and smaller samples and saw some deviations from Boltzmann kinetic theory, right, which were attributed to quantum coherence of electrons. But electrons were thought, nevertheless, as individual, well-defined quasiparticles that were propagating. So this is sort of having its roots in the Fermi liquid theory. You have electrons as well-defined objects in a metal, and then they're subject to disorder, interactions, and whatnot. But in some sense, these interactions are extrinsic. They're not a part of your, so like phonons. Phonons are not part of the electronic system, right? There's something else. And so you can then adopt a point of view that you can start with a non-interactive system of electrons, put it into a strong magnetic field and disorder, and this system by itself exhibits an integer quantum Hall transition. So it's already a good basis for your more realistic approaches. And that system belongs to the class of Anderson localization transitions, where essentially the transition is driven by localization physics, right? This disorder is essential in this case. And then you can try to maybe, and I will focus on this problem a lot in the next talk on Thursday, because it's kind of important and interesting in itself. But then conceptually, you can try to add interactions on top of this picture and ask whether they're relevant or irrelevant. Or even before that, you can treat them perturbedly and just ask, what do they bring? What kind of dephasing rates they introduce? What happens to so if electron has some inelastic sketching of a phonon or of another electron, then its energy is changing and its phase is breaking. So that's what leads to phase breaking. So you can sort of study phase breaking mechanism, not phenomenologically like in quantum phase transition picture, but microscopically, just literally computing things, right? And so that leads to all kinds of dephasing mechanisms and dephasing rates that typically diverge. Sorry, the phase breaking times or dephasing times diverge, and the rates go to zero as temperature goes to zero, not in linear fashion. So remember that this dephasing rate in the generic quantum critical point was t, not t to the p. But here some exponents appear, p, and the corresponding length has some exponent, not z, but z sub t, that is related to this new exponent p, and generically it's not equal to z, okay? So, and this p is mechanism specific, so you can have different dephasing rates, different quantum, so different dynamical critical exponents for the same system. You can have several different z sub t, depending on the mechanism that dephases your electrons. And so whether this picture is important or not, or whether the generic quantum phase transition picture is true or not, depends on whether the interactions are relevant or irrelevant at the non-interacting fixed point. So if they're relevant and grow, then you're back to the generic case. If they're irrelevant, so they die out, and this physics becomes important and visible, but nevertheless, they're kind of still changing the scaling of the whole system. I'll show it in the next slide. Now, this question itself, so to answer question whether a given interaction is relevant or irrelevant to non-interacting fixed point, you have to sort of set up some RG scheme and do some computation. And so in this case of the interquantum transition, for example, you can only rely on some numerics to do this computation because we don't have a good theory even for the non-interacting case. As I will tell you more about it, there's no theory for the integer quantum fold even in the non-interacting case, I think. No well-developed theory. No, Anyway, but numerics tells you that the short-range interactions are irrelevant, and long-range interactions such as Coulomb are relevant. So now, from the point of view of experimentalists, you can try to actually do some gating of your system to sort of cut off the long-range Coulomb interaction, and some partial results to this in this direction exist, but it's kind of hard in the old days when you had the semiconductor heterostructures. The gates could not be placed very close to the system, right? But now with graphene, I think this is a real opportunity for people to do this. And so some experimentalists are thinking about, so revisiting this whole story of difference between the short range versus long range interactions. Okay. Now, so subsequent work on this topic revealed the following story. Even when interactions are irrelevant, they are responsible for the non-trivial scaling with temperature. So if you literally want to study what happens in a non-interacting system at finite temperature, you'll get trivial results. The point is that the basic non-interacting physics that I'll, again, cover in a lot more detail is that most of the states are localized and do not carry any current or cannot transmit any electricity, and only certain single particle energies correspond to current carrying states, and just the measure of the states is too tiny to produce any finite conductivity at finite temperature. So conductivity at finite temperature will be zero in a non-interacting system. Not what one observes, certainly. But if you take into account irrelevant interactions, they're in some sense dangerously irrelevant because they lead to some discontinuity in the scaling functions. And what happens is that if you go through the analysis, what really happens is that the appropriate scaling form should have the ZT coming from the interactions that governs the temperature scaling but the usual Z that controls the frequency scaling. So if you think about now what controls the width of your transition, it's one of the two quantities if you impose just the temperature and the frequency. And of course, electric field, finite size system, and so on can be added here. But you see that the temperature scaling and the frequency scaling can be actually different in this case. And if you go through this whole analysis, these new exponents, ZT and P, in the dephasing rates, are determined by the scaling dimension of the interaction strength. So in some RG scheme, you can ask what's the scaling dimension of the interaction strength, and flows, and either diverges or... So in this case, when we talk about short range, it's irrelevant, so the scaling dimension is negative, and this alpha determines all these exponents here. Well, so this alpha, being the property of a non-interacting fixed point, should be subject, well, should relate to some scaling dimension of some operator in that non-interacting field theory, non-interacting system. So the question for the non-interacting story is to find this alpha, for example, right? And so, unfortunately, we don't have that theory under control. We don't have a, controllable approach which was predictive powers, but to give you numbers. So, but conceptually, what you do, you have to sort of think about the matrix elements of the interaction in the Slater determinant states, right? And so ultimately, what you want to do is you want to take the exact eigenfunctions of your single particle problem in the presence of disorder and strong electric field, and study the scaling behavior of this kind of objects, right? So you want to know how the correlation functions of wave functions scale with distance, for example. And that's what determines ultimately this exponent. And through it determines all this physics of short range quantum Hall transitions. And well, okay, so I'll come back to this in my next lecture. Today, let me mention another story, is that, so far I've been trying to explain more or less the integer quantum Hall transitions, but we saw that fractional quantum Hall transitions have the same exponents, which this is a completely amazing story, because fractions, of course, are governed by strong interactions, and that's nowhere close to non-interacting fixed point. But the theory of composite fermions actually explains it, and early on, soon after the Jinendra introduced the composite fermions, he teamed up with Steve Kilson and Nadine Trivedi, and they proposed that this also explains the scaling and the fractional quantum Hall particle transitions, because more or less, once you know that attaching vortices to electrons leads to these Jane sequences, I mean, you can think now with the transition between integers in nu CF being analogous to transitions between fractions of nu. So, for example, if you attach two vortices, then the integer quantum Hall transition between 1 and 2 maps to the transition between 1/3 and 2/5. And so they should kind of, so if you think about composite fermions as almost non-interacting, then it should be the same physics, more or less. And much more recently, there was a much more serious numerical work where, well, I hope Jinendra will talk about this, maybe tomorrow, right? So where you, so details, I'm not sure I'm in a position to discuss them, but essentially, it's easy to more or less say that, okay, since you have this mapping between the states, maybe the transitions also are mapped to each other. But it's a totally different story, because you have to generalize this to a disordered system. So the original composite fermion story is not taking into account the disorder, because just the wave function, so more or less Laughlin wave function, that is for a clean system, right? So how to introduce disorder and do it reliably is the subject of this laser paper, and I hope Jinendra will explain it. All right, so now let's see. in some sense, this is I have 5 minutes, right? Let me now abandon this overall phenomenological description and try to actually focus on something more microscopic. And I will take this approach of the mesoscopic physics. So I will actually be thinking about the non-interacting problem. And so let's start talking about this. So if you start with a single electron in the magnetic field and a random potential, this is very simple Hamiltonian, just a single particle quantum mechanics. So what can be interesting here? So if you remove the disorder potential, then you get Landau levels, which are equally spaced and infinitely degenerate in an infinite system, right? Now, the disorder, when you introduce it, it breaks this degeneracy and localizes most of the states. So I'm talking about phenomenology that has been worked out by many people. I'm not really providing any references here, but that's what we think is happening. So most energies correspond to localized states, and the dashed line here shows the localization length that is divergent upon approaching these critical energies. Okay? So viewed from this point of view, the quantum Hall transition is an Anderson transition between two localized states separated by some kind of extended state. So it's a localization-delocalization transition. All right? Now, it's a non-interacting quantum phase transition. And for this one, we can definitely know what Z is. So that's one result at least known exactly, because the relevant energy scale here is just the mean level spacing in the localization volume. And so if the density of states is not critical, it's a smooth function across this transition, you can just estimate the this energy spacing as 1 over psi squared, where psi is the localization one. And so it's just coming from the kinetic energy being k squared over 2m, more or less, right? That's quantum mechanics, single particle quantum mechanics, non-relativistic single particle quantum mechanics leads to z equals 2. Okay, now one caveat to this story is that once you start thinking about disorder, anything you can think of, any observable conductance of a sample is a random quantity. It really has strong fluctuations from sample to sample. And what really has to be done, one has to think about distribution functions of all observables, right? And that's a tall order. I mean, we don't even really have theory for mean values and moments, only, qualitative understanding, but a full theory would require the distribution functions. So that's just a caveat. Now, okay. Well, let me just say that once we talk about Anderson localization or single particle physics, you can ask can you classify different systems and different Anderson transitions? Indeed, you can. And Altman and Cernbauer did this in 1996. Since then, this classification has become central to the understanding of topological nature, topological phases of matter, which are also classified according to the same classification. But let me just mention, without just explaining all this story in detail, let me mention that the interquantum Hall effect would be sitting in one of these classes, but there are similar transitions for quasi-particles in two-dimensional disordered superconductors that would affect spin conductivity and thermal conductivity of those quasi-particles. And those called spin quantum Hall effect and thermal quantum Hall. And these are important cousins of the interquantum Hall effect that I'll be having in mind. And final slide, let me just flash this before we continue next time. The difficulty with all this story is that even in the non-interacting picture, there's no small parameter. We don't have any controllable way of doing any kind of RG, though we expect a conformal field theory maybe to be relevant here. And then, okay, I'll start with this slide next time.